Hi, welcome to my presentation. I'm Cheon from MLB Lab at Korea University. Today, I will present inversion-based latent Bayesian optimization. Bayesian optimization aims to search for optimal input that maximizes the objective function f, which is assumed a black box and expensive to evaluate. To solve this problem, we first statistically estimate the objective function f with surrogate model G. Next, given the surrogate model, we select the next quantify the acquisition function alpha. We repeat these steps until the Oracle budget is exhausted. Even though BO shows superior performance over continuous input space, applying it over discrete input space is quite challenging. To address this issue, latent Bayesian optimization has been proposed. Given the objective function f and the pre-trained decoder p zeta, LBO aims to search optimal latent vectors that maximize the composite function of f and p zeta. To solve this problem, we first encode discrete data into latent space. Next, same as standard BO, we train a surrogate model and select the latent query by acquisition function. Some LBO works restrict search space by trust region to handle the high-dimensional search space. In step 3, we decode the latent query vector by decoder p zeta. Finally, we evaluate the discrete query data by black box function f and repeat this process until the Oracle budget is exhausted. In our paper, we identify two novel challenges in LBO. First one is a misalignment problem. Since the objective function in LBO is the composite function of the black box function f and decoder p zeta, the surrogate model should learn the relationship between this decoder triplet. However, we cannot directly find the latent vector z that can generate given target discrete data x. Instead, most prior LBO employed a surrogate model trained with this encoder triplet. The surrogate model trained with an encoder triplet fails to estimate the objective function correctly, resulting in a suboptimal outcomes. We name this the misalignment problem. The second challenge in LBO is about trust region anchor selection. Previous methods select the trust region anchor as the current optimal point. However, this approach does not consider whether the trust region contains a good latent point. To handle these two challenges in LBO, we propose InvBO, a plug-and-play module for LBO. The first component of InvBO is an inversion method. The goal of this inversion method is to generate a decoder triplet without any additional Oracle call. As shown in this figure, previous work generates a decoder triplet by consuming additional Oracle calls. However, our inversion method generates decoder triplet without any additional Oracle calls by searching the latent vector that can generate already evaluated discrete data. With a pre-trained frozen decoder, we can obtain a decoder triplet by solving this equation. Specifically, we iteratively search the solution with a gradient descent algorithm as shown in this pseudocode. Also, we theoretically show that our inversion method can reduce the upper bound of GP prediction error within the trust region. The second component of InvBO is potential aware anchor selection. The goal of this method is to select a trust region anchor jointly considering the objective function and potential ability of the trust region, which is defined as the capacity to contain latent points that can enhance the optimization performance. To quantify this, we use the acquisition function. Our pass method consists of 4 steps. In the first step, we compute the potential score of each trust region by the acquisition function. In the second step, we scale the potential score according to the objective value. Next, we compute the final score with objective function value and scale the potential score. Lastly, we select the anchor with the highest final score. Our InvBO was evaluated on 9 different benchmarks. The figure shows applying our InvBO to cover one of the previous LBO methods achieved the best performance in all 7 tasks. On this page, we compare the performance of the Gaussian process trained with an encoder triplet and decoder triplet. This experimental research provides strong evidence of the effectiveness of the inversion method. Lastly, we compare diverse trust region anchor selection method. It shows that rather than considering solely, jointly considering the equation function and objective function could enhance the optimization performance. In summary, we propose inversion-based latent Bayesian optimization, which is called InvBO, a plug-and-play model for LBO. Next, we introduce the inversion method that inverts the decoder to find the latent vector for generating the decoder triplets. Next, we present the potential-aware trust region anchor selection that considers not only the corresponding objective function, but also the potential ability of the trust region. Finally, applying InvBO over diverse prior LBO works show a large performance gain and achieved state-of-the-art performance on 9 different tasks. For access to open source and main paper of our InvBO, we provide QR codes. Thank you for listening.